Inertia is basically resistance to change. So objects in motion want to stay in motion, and objects at rest want to stay at rest. Our first example is simply to take a card and put some coins on it and place it on top of a cup. When you flip the card, the coins will want to stay where they are, like in this picture, while the card goes flying out. The coins have inertia. A similar example is where you take a tablecloth with dishes on it and you slide it out from under the dishes. I'm going to demonstrate this with a beaker and a tablecloth and a paper towel. And what you'll see is when I slide the paper towel, the beaker wants to stay in place. To be fair, this doesn't always work. Let me show you this example. Same demo, same exact everything else, but this time there's a little bit of resistance when the back of the paper towel breaks. In the next example, a piece of chalk is placed on top of a metal ring, a loop, above a Erlenmeyer flask, like a bottle. When you remove the metal ring quickly, the chalk falls into the Erlenmeyer flask. When I reload the activity one more time, this time with a smaller Erlenmeyer flask, and we're going to slow it down right at the moment the ring gets moved. Pretty cool stuff. In the next demonstration, a block of wood has a wooden dowel sticking through it. We want to determine which way the block will move if we bang on the wooden dowel. I've marked the top and the bottom of the dowel where the block will be placed. Then I'm going to bang on the dowel, and when I do, we want to know, does the block move down or up, or does it stay in place? So in fact, the block really doesn't move. It's the dowel that pushes through the block. There's a typical question that goes, if you have a ball in a cart and you move the cart, what does the ball do? Well, we'll demonstrate this using a rolling cart and a track. When we move the track, the cart stays in place. If we do this in slow motion in the opposite direction, we'll notice that, well, it doesn't always stay in place. Another question that asks, what happens if we have two strings attached to a weight? One above the weight that is hanging from a bar, and one that is below the weight hanging from a bar. If we pull the string at the bottom in different manners, we get two different responses. For instance, if we jerk on the string quickly, the bottom string breaks because the mass has inertia. It holds the motion away from the top string. But if we do it slowly, steadily, now there's two forces on the top string, and the top string breaks. This demonstration helps to show relative motion. For instance, what happens to an object that's in a car. If we're stationary, you can see our yellow ball being fired from its launcher straight up. As long as it's not moving, it just goes up and straight down. Now, if the cart is moving and we launch the ball, what does the ball do? Does it still go straight up and down, or does it travel with the cart? There it is. And you can see that the ball travels up, but with the cart. It goes with it. It moves at the same speed. Watch it one more time. Launched and comes right down where the launcher is. The last demonstration is one that I do in class that often ends up with me doing more damage than I should. The idea is this. If we have a massive object like an anvil, or in this case several weights, and we bang it with a hammer, and you can see I am now hammering on the weights while my hand is under them. I put a cloth over my hand so I don't scratch my hand on the weights. I can assure you there's lots of pressure on them, but as you can see, my hand is fine.